So let us start again. So we have understand the null hypothesis and alternative hypothesis used in Dickey-Fuller test. Now question is how to carry out this test. To carry out this test, we have to estimate the model first, as I have mentioned earlier. So you have to estimate either equation 1, 2 or 3 or alternatively 4, 5 or 6
Recording.
by applying OLS. And suppose phi 1 hat is the estimated value. So under null hypothesis, the t statistic look like this: phi 1 hat minus expected value of phi 1 hat, and if you know the basic econometrics, expected value of phi 1 hat is equal to phi 1, and under null hypothesis, phi 1 is equal to 1. Therefore, this is the mean value of phi 1 hat. So t statistics looks like this: phi 1 hat minus 1 divided by standard error of phi 1 hat, which is equal to rho hat divided by standard error of rho hat, because we have defined rho is equal to phi 1 minus 1. Okay, so this is the test statistics used in Dickey-Fuller test, and it looks similar to the t statistics we have used conventionally. Now, if we estimate phi 1, the estimated value phi 1 hat is equal to this. How to get? Just try to remember the basic formula for beta hat in simple linear regression model. Beta hat is equal to sum of xy in the numerator divided by sum of x square. So sum of xy means sum of xy. In our model, yt minus 1 is similar to x, yt is similar to y. Because yt minus 1 is a regression, yt is a regression. Okay, so phi 1 hat, the OLS estimates of phi 1 hat would be equal to sum of yt minus 1 into yt divided by sum of yt minus 1 square. And this is similar to the beta hat equal to sum of xy divided by sum of x square, as you have in a simple linear regression model. Clear? Now, if we manipulate this value, that is, just substitute the value of yt here. Okay, so suppose we are estimating equation 1. So in equation 1, yt is equal to phi 1 yt minus 1 plus epsilon t. So just put the value of yt here, and after some simplification, you will get the result like this: phi 1 hat is equal to phi 1 plus this component. And this is similar to the result you have in a simple linear regression model. Just try to remember, beta hat is equal to beta plus sum of just a minute. Beta hat is equal to, you know, beta plus sum of xi into ui divided by sum of xi square in a simple linear regression model. So similarly, we have the result like this in our case, because I have mentioned yt minus 1 behaves like x, the regression, epsilon is a random error term. So phi 1 hat is equal to phi 1 plus this component. If you take expectation on both sides, expected value of phi 1 hat is equal to phi 1, because expected value of this term equal to 0. Because here we have epsilon t, and expected value of epsilon t by assumption is 0. Therefore, this component is 0. So the mean value of the estimated value, OLS estimates, is equal to phi 1. And this is also similar to our results we have in a simple linear regression model. And the variance of phi 1 hat, you can understand the value of it just keeping in mind the value of variance of beta hat. What would be the formula for variance of beta hat? Try to remember, the variance of beta hat is equal to sigma square divided by sum of x square. So in this case, the value will be sigma square divided by sum of x square, because x means yt minus 1 here. Okay. Now we simplify this expression in this way. Sigma square we are retaining the same in the numerator. Denominator is written in this way, t into this divided by t. Why? Because this part will be the variance of yt. Okay. So we can write sigma square in the numerator as it is, in the denominator t into this part is the variance of yt, and try to remember variance of yt is equal to sigma square divided by 1 minus phi 1 square. So your result ultimately variance of phi 1 hat is equal to 1 minus phi 1 square divided by t. So you have to go through the derivation. I have for simple reason skip some steps. So by following the detailed steps, you will get the value variance of phi 1 hat is equal to 1 minus phi 1 squared by t. And the steps are very simple. Start with the basic definition of variance of beta hat. Variance of beta hat, because phi 1 hat is similar to beta hat in our simple linear regression model, is equal to sigma square divided by sum of x square. Sum of x square means in our case sum of yt minus 1 square. And we manipulate the denominator, keeping the numerator as it is, just by multiplying t and dividing by t. After dividing by t, this component becomes variance of yt. And the value of variance of yt we have already derived is equal to sigma square divided by 1 minus phi 1 square. So the variance of phi 1 hat ultimately becomes 1 minus phi 1 square by t. So we have to keep in mind two things. The mean value of phi 1 hat is equal to phi 1. The variance of phi 1 hat is equal to 1 minus phi 1 square by t. What is phi 1 hat? Phi 1 hat is the OLS estimates of phi 1. What is phi 1? Phi 1 is the coefficient for yt minus 1. We are interested with in testing unit root. Okay. And the statistics used in Dickey-Fuller test is similar to the t statistics we have, that is phi 1 hat minus 1 divided by standard error of phi 1 hat. So to understand the testing procedures in Dickey-Fuller, we need to understand the value of t we have got here. So value of t is equal to phi 1 hat minus 1 divided by standard error of phi 1 hat. And in conventional case, you know, for large number of observations. So here the number of observations is counted in terms of the number of times, because we have a time series data. So if you have a longer time series, if you have a longer time period, if you have total time period is sufficiently large, in that case, you know, t distribution is converted to the normal distribution. So we can write in this way, for a very large t, t means total time span in our data set. So if we have larger t, that is total time span is very large, t distribution will be the standard normal in asymptotic sense. That is the T statistics we have defined here in equation 7 will be a standard normal distribution in asymptotic sense. Okay. Now, for standard normal distribution, you know the mean value is 0, variance is 1. Now, let me look at what would be the distribution in our case. In our case, the statistic is phi1 hat, and on the basis of phi1 hat, we have constructed the T statistics. And the distribution of phi1 hat depends on the distribution of epsilon T, the random disturbance. If we assume the random disturbance distributed normally with mean value 0 and variance sigma square, in that case, phi1 hat will also be distributed normally. And its mean value will be phi1. We have calculated just now here. Expected value of phi1 hat is equal to phi1, and its variance is equal to 1 minus phi1 square by T. So the distribution of phi1 hat can be written in this way: phi1 hat distributed normally with the mean value phi1 and variance 1 minus phi1 square by T. Now, স্ক্রিন হ্যাং করবে না, ওটা ওই নেটের নেট। Have you reconnected? Have you got it again? I'm sharing it. Is it clear?
No.
The internet connection is unstable. That's why some problem appears. Network is very poor. Okay, try to understand as possible. So we have the distribution of phi1 hat. Is it? Hello. 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 Am I audible?
Yes, sir. Yes.
হ্যাঁ স্যার, এবার দেখা গেছে আপনাকে। হ্যাঁ, স্ক্রিনটাও দেখা যাচ্ছে।
সামনের দিন আমরা দিনের
স্যার
বেলা
যদি একটু স্ক্রল করে দেখান তো, স্ক্রল করলে যদি মানে দেখান তাহলে যদি বোঝা যায় যে স্ক্রিনটা আটকাচ্ছে কিনা। হ্যাঁ স্যার, ঠিক আছে।
হ্যাঁ স্যার, ঠিক আছে, ঠিক আছে, ঠিক আছে।
আচ্ছা, সামনের দিন আমরা দিনের বেলায় বসবো, সন্ধ্যের দিকে নেটের প্রবলেম হচ্ছে, ঠিক আছে? আমি জানিয়ে দেবো তোমাকে।
ঠিক আছে।
So let me continue. So this is the estimated value for phi 1 and its distribution looks like this. Now under null hypothesis, value of phi 1 is equal to 1. So under null hypothesis, the mean value of this distribution will be 1, and the variance, if you said phi 1 is equal to 1, the variance becomes 0. Okay. So under the null hypothesis, the distribution of phi 1 hat will be normal with mean value 1, variance 0. But we need, for meaningful inference, the distribution should be normal with mean value 0 and variance 1. So if your distribution has variance 0, the distribution will be useless at all. So in this case, the distribution of phi 1 hat does not make any sense. So this is the major problem in the Dickey-Fuller test if we apply the conventional t statistics. Have you understand the basic points what I try to tell you? Conventionally, we use t statistics like this for testing of hypothesis. Now in the Dickey-Fuller test, if we use this type of statistics, some typical problem will appear. What is the problem? In this case, the distribution of phi 1 hat has mean value 1, variance 0 under null hypothesis, because phi 1 hat has mean value phi 1, variance of phi 1 hat is equal to this. So after substituting phi 1 is equal to 1 under h naught, you will get the mean is equal to 1, variance is equal to 0. So if a distribution has 0 variance, the distribution has no meaningful interpretation at all. For that reason, we cannot use the conventional t distribution in the Dickey-Fuller unit 2 test. You have to keep in mind. So we cannot use the t distribution in the Dickey-Fuller testing. So what is the way out? Way out is we have to find out a new kind of distribution which is roughly similar to t distribution, because t distribution is not applicable for the Dickey-Fuller statistics, because we have this kind of problem if we use the t statistics. Now later on, after a lot of exercise, some people have derived a new kind of statistics just by examining the random behavior of phi 1 hat, and reached a conclusion like this: the phi 1 hat follows a distribution, not exactly t distribution, but t type of distribution. And t type of distribution is obtained by following the behavior of the randomness as observed in the molecular motion. So by observing the random behavior of the molecule, that is the that follows the Wiener kind of distribution. So by utilizing the behavior of Wiener distribution, we have to find out the distribution of phi 1 hat to carry out the Dickey-Fuller test. For that reason, when you performing Dickey-Fuller test with data in your lab class, you cannot use the t statistics. You cannot use the critical values as used in normal distribution or in the t distribution. For Dickey-Fuller test, you have to have a new type of critical values, new type of theoretical values based on the new distribution, but this new distribution also roughly similar to t, but not exactly equal to t distribution. Okay. So this is the basic problem for Dickey-Fuller test. Now let we come to the another problem. We have already mentioned the Dickey-Fuller test is related to AR1 only. Dickey-Fuller test captures the presence of unit root if your series follows AR1. But in reality, there is no guarantee that the series you have always follow AR1. Okay. If your series follows higher order of autoregression, we cannot use the Dickey-Fuller test in this format. So what is the way out? Way out is we have to convert the higher order autoregressive process into AR1. And after converting AR1, we can apply the Dickey-Fuller test. Okay. And this part is called the augmented Dickey-Fuller test. So augmented Dickey-Fuller unit root test is applicable if your data, if your series follows higher order autoregression. Okay. So how we can perform Dickey-Fuller test for higher order autoregression? For example, suppose we are considering AR2 process. AR2 process, you know, looks like this. Yt is equal to phi naught plus phi 1 yt minus 1 plus phi 2 yt minus 2 plus epsilon t. So this is AR2. So we cannot apply Dickey-Fuller test for this AR2 module because by definition AR2 deals with only AR1. So if we want to apply Dickey-Fuller test, we have to convert this AR2 model into AR1. How to convert it? For this reason, we need a simple manipulation. What kind of manipulation? Just try to understand this step. We have AR2 in equation 11, yt is equal to phi naught plus phi 1 yt minus 1 plus phi 2 yt minus 2 plus epsilon t. Now, we are manipulating this relation in this way. Write down the left hand side as it is, yt is equal to phi naught as it is. Now, do not write this one. Try to concentrate on this term. We originally have phi 2 yt minus 2. And the presence of this term makes the process of yt AR2. So we have to eliminate the effect of this term on y2. How to eliminate? Now look at this term. How to get it? Just if you simplify this, just multiply minus phi 2 into within bracket, you have minus phi 2 into yt minus 1 plus phi 2 into yt minus 2. So plus phi 2 into yt minus 2 we already have in our original form. But we do not have minus phi 2 yt minus 1. Okay, I will explain why we need to consider minus phi 2 yt minus 1. But before it, try to understand the adjustment process, how to adjust it. So originally we do not have minus phi 2 yt minus 1. For that reason, we have to add phi 2 yt minus 1. So equation 11 is similar to this. Just try to understand it. If you expand it, you can reach at 11. So how we can write equation 11 in this format? The second component can be written in this way. If you go through the next step, in the next step, we have subtracted yt minus 1 from both sides. So left hand side becomes delta yt. Phi naught still remains phi naught. Now this term, phi 1 plus phi 2, originally we have the coefficient for yt minus 1. But again, we have subtracted yt minus 1 from the both sides. So we have the coefficient for yt minus 1 in this way, phi 1 plus phi 2 minus 1. Do you understand this step?
Yes, sir.
Okay. So delta
স্যার
yt
বিটাটা কি করে আসলো স্যার?
কোনটা?
বিটাটা
বিটাটা ধরে
বিটা?
নেওয়া হলো minus phi 2 is equal to beta. Minus phi 2 কে আমরা
Okay,
beta ধরে নিলাম. And we have denote phi 1 plus phi 2 minus 1 is equal to rho. So after denoting phi 1 plus phi 2 minus 1 is equal to rho and minus phi 2 equal to beta, we
স্যার
have,
ওর বিটা 1 হবে না
sorry,
স্যার বুঝে এই যে ডেল্টা বাই টি মানে ইকুয়েশনের সেখানে বিটা 1 হবে না ইকুয়েশন 12 এর আগের ইকুয়েশনটা যে বিটা
oh
লেখা
sorry,
আছে
sorry, এটাকে beta 1 করে নাও, এটা typo. This should be beta 1. বিটা আর বিটা 1 এগুলো তো সব ধরে নেওয়া। বিটা 1 লিখছি তার কারণ আছে, পরবর্তীকালে যখন আমরা মডেলটাকে এক্সটেন্ড করব, so to keep similarity, change it at beta 1, not beta. So this beta 1 and this beta 1 is same. Okay. So this is an error here. So what we have done, equation 11 is converted into equation 12. Now equation 12, if we look at the behavior of equation 12 is AR1. Just look at it. Equation 11 was AR2. We have converted AR2 into AR1 just by adding this component. This component is called the augmented term. That's why this model is called augmented Dickey-Fuller. So AR2 model can be converted into AR1 by adding one augmented term. So as we need one augmented term to convert AR2 into AR1, the AR2 model, which is in original form AR2, can be called, it is ADF1, that is augmented Dickey-Fuller of order 1. This is because this AR2 model can be converted into AR1 just by adding one augmented term. Okay. So the model is augmented Dickey-Fuller model, and if yt follows AR2, we need one augmented term to convert it into AR1. Therefore, equation 12 is called ADF of order 1, augmented Dickey-Fuller of order 1, because we have incorporated one augmented term here to make it AR1. Now again, take another example, AR3. And it would be better if you try independently just now how to get these steps in your exercise book, just by following these steps we have followed here. So write down AR3 in this way. Yt is equal to phi naught plus phi 1 yt minus 1 plus phi 2 yt minus 2 plus phi 3 yt minus 3 plus epsilon t. This is AR3. Now start manipulation from the last term. How to follow? First of all, we have to convert this term into in difference form. So for that reason, we have to change this component into yt minus 2 minus yt minus 3. So for that purpose, you need minus phi 3 yt minus 2, which was not in our original form. So we have added minus phi 3 yt minus 2. So you have to add plus phi 3 into yt minus 2 in the earlier component. So this part becomes delta yt minus 2. Similarly, you have to change this part as delta yt minus 2. So to change delta yt minus 2, you need here phi 2 plus phi 3 into yt minus 1. Because here we have jumping one step to save the space. So if you follow the detailing steps, you cannot get directly in this form. So to first of all change the third component in this form and accordingly adjust your equation. In the next step, change the second component into this difference form and adjust the necessary components again. So ultimately you have in this form delta yt is equal to phi naught plus phi 1 plus phi 2 plus phi 3 minus 1 into yt minus 1 plus beta 1 delta yt minus 1 plus beta 2 delta yt minus 2 plus epsilon. And you can write in compact form delta yt is equal to phi naught plus rho yt minus 1. Rho means we have denote this component together as a rho plus beta 1 delta yt minus 1 plus beta 2 delta yt minus 2. So after incorporating these two terms, the AR3 shown in equation 13 could be converted into AR1 shown in equation 14. So to convert AR3, we need to incorporate two augmented terms. Okay, so after incorporating two augmented terms, AR3 can be converted into AR1. So in this way, if you have originally ARP series autoregressive of order P, then you need to incorporate P minus 1 augmented terms. So after adding P minus 1 augmented terms, you can convert ARP process into AR1 process, which looks like this. And after converting AR1, you can apply Dickey-Fuller test. This is called the augmented Dickey-Fuller test. So augmented Dickey-Fuller test is nothing but the extension of the methodology which is applicable for higher order autoregression. We need it simply because Dickey-Fuller test by default takes care of only AR1. So if we want to apply Dickey-Fuller, we have to change the higher order autoregressive model into AR1. After changing it, we can apply Dickey-Fuller. For changing higher order autoregression into AR1, we need to add some components. Those components are called the augmented terms. And the model we have the augmented Dickey-Fuller test. And the testing procedure is similar as we have shown in the null hypothesis, alternative hypothesis, because now we concentrate on rho. So our null hypothesis becomes H naught, rho equal to 0, and alternative rho less than 0. Okay. We can extend further by considering the ARMA PQ model. And you know ARMA PQ process can be expressed as autoregressive of order infinity, like this. Autoregressive of order infinity, so it would be augmented form in this way. This is AR1 with infinite number of augmented terms. And obviously it is difficult to estimate in reality, but we can estimate this model after some adjustment. So we have a few seconds left for this session. So we can start again to look into further issues relating to the Dickey-Fuller test or augmented Dickey-Fuller test in the third session.